large appetizer of the session, afternoon session, which is about active galactic nuclei, with the invited speaker Matteo, which will talk about, finally, a short title for me, High Resolution Spectroscopy of AGN.
Okay, thank you. High resolution spectroscopy in X-rays has been key to make advancement in our understanding of accreting supermassive black hole, active galactic nuclei. And this is essentially for three reasons. The first one is that the accretion disk that we believe is surrounding a supermassive black holes comes very close to the black hole, at the distance that maybe is of the order of a few or even one gravitational radii. So this means that when you look at an AGN, you are probably looking at the system which is an ideal laboratory to test the behavior of matter for general relativity in the strong gravity field regime. Now, Javier Garcia, the first day, explained us how we do that. The red spectrum that I show here is the theoretical expectation of what an accretion disk, the spectrum of an accretion disk is when illuminated by X-rays of a corona. And this spectrum is full of emission lines coming from fluorescence and recombination transitions. But we will never see that if this is produced close to a black hole, because all these features will be blurred by special and general relativity effects that are needed, inescapable if you are close to the black hole. We would be seeing something like this, where all these features are blurred. And this blurring is dependent, among many things, on the black hole spin. And this is the basis of the only method we are aware of in this moment to estimate the spin of accreting supermassive black holes. Now, I could give a full 2 hours talk on to what extent these measurements are precise and accurate. My take on is that probably only with New Athena, we will be able actually to tell what are the true systematic errors associated to these measurements. But this measurement is true on when these measurements will become fully reliable. They will be very important because they are sort of fossil remnant of the evolution of a galaxy. If a galaxy goes through a prolonged phase of coherent accretion, the spin will be maximum. Whereas if a galaxy grows through several phases of merging, most likely the end result of the black hole spin will be a spin close to 0. Now, this has been traditionally considered a field for CCD resolution spectroscopy, because the blurring due to special general relativity effects essentially acts on a range of energy which is of the order of at least a few hundreds electron volts. So why do you need high resolution spectroscopy? Indeed, in principle, you don't need high resolution spectroscopy, but there have been a few measurements with the RGS of this kind of very broad and asymmetric emission lines. And whenever these measurements have been possible, they are consistent with the expectations. They are lines that are produced within a few tenths of gravitational radii from the black hole event horizon, and the density that you derive from of the accretion disk is actually consistent with the expectation of the relativistic version of a Shokura-Sunyaev accretion disk. But this is one of the fields where indeed only microcalorimeter measurements will actually be able to tell what the real story in terms of observation is. A second reason why high resolution spectroscopy in X-rays is key is it allows us to overcome a fundamental problem when we try to understand AGN. AGN are simply too small in the sky. They cannot be resolved, and they will not be resolvable for at least another generation of observation of instruments. So, and at the same time, we know, or we at least, well, we suspect that the distribution of gas and dust in the nuclear region of AGN is extremely complex, with lots of components that actually correspond to different physical conditions, and the very complex dynamics. So high resolution spectroscopy allows us essentially to do milliseconds indirect imaging by characterizing the gas on various spatial scales. And the important spatial scale here are the location of the innermost stable orbits of the accretion disk, the size of the X-ray source, the scale where gas is in viral motion, so essentially the dynamics of the gas is dominated by the gravitational potential of the black hole, and the dust sublimation radius. Now, studying virial clouds is something that optical astronomers have been doing for decades. In fact, the detection of lines with a width of a few thousand kilometers per second has been the main tool to identify active galactic nuclei in galaxy through optical spectroscopy. But thanks to high-resolution spectroscopy in X-ray, we can now measure the X-ray counterparts of these clouds. And more interesting, probably in a mid-term perspective, surely more interesting for CRISM, we already able now, and we will be able much better in the future, to make reverberation mapping measurements with X-ray lines. So to measure the response of the X-ray lines to variation of a continuum, which is a technique that enables to do in the same time two things. On one side, it gets a constraint of the geometry of these clouds, which is, of course, completely unknown because they are unresolved. And on the other hand, to get a glimpse, an estimate of the mass of the black hole, which is otherwise not so easy to get for objects where the surrounding gas and stars are not resolved. Now, a key observational feature in this measurement has been the K-alpha iron line, which is basically ubiquitous in the X-ray spectra of AGN. And whenever you can make a constraint on where the iron K-alpha line is coming from AGN, is always invariably coming from a region which is commensurate to the location of the virial broad clouds that are responsible for the broad line emission in the optical. And it's always lower than the location of a dust sublimation radius. Now, this is in this plot, in this compilation, recent compilation, the location of the K-alpha line are the red points. And you see a lot of green downward arrows in these plots, which represents the upper limit on the location of the X-ray emission coming from Chandra imaging. And the fact that they are arrows is actually suggesting you that these are upper limits, which it just confirms you the fact that AGN are basically unresolved in X-rays. But you also see two bars, and these bars are not upper limits. They are somewhat evidence that we can actually see in some object resolved extended emission at the iron K-alpha line in AGN. And I will come back later to why this is important and is potentially interesting. And there is a third reason why high-resolution spectroscopy in X-rays is a key for our understanding, not only of AGN, but in general, the co-evolution, the cosmological co-evolution of accreting black hole and their host galaxy, which is AGN feedback. Now, this plot has nothing to do with X-rays. It's a relation between, on the x-axis, a quantity which is related to the size of a galaxy. In this case, is the velocity dispersion of the stars in the bulge of a galaxy. And on the y-axis is the mass of a supermassive black hole at the center measured through different methods, most notably reverberation mapping in the optical. And there is a very tight correlation. This tight correlation is not just to the fact that big things go together. It's probably a strong evidence of a causal relation between black hole growth and star formation that we call AGN feedback. And the hypothesis on which we have been working for a couple of decades is that this AGN feedback is carried by powerful AGN outflows. So what are AGN outflows? So whenever you point the RGS or the ATG or whatever spectrometer towards an AGN, invariably, at least 75% of the time, and the number is not by chance, you actually look at very strong absorption lines. And these absorption lines are coming from the wide range of helium and hydrogen light transitions of metals, from carbon to iron, And as said, they have been seen in at least 3/4 of a well-defined sample of local AGN in the local universe, and they correspond to a very wide range of physical conditions. Velocity going from a few thousand to a kilometer per second to a fraction of the speed of light, column density going from 10 to the 20 to 10 to the 24, and ionization states that are very wide. In fact, that's of course already understandable if we have transition going from carbon to iron. Now, we understand now, thanks to extensive observations with RGS, with the LETG, with the HETG, the physics of these outflows. We know how actually to calculate the absorption measure distribution of many of these outflows, which is essentially the column density of each of the ionization components of these outflows that covers, as I said, a range in ionization parameters from a few tens to thousands. Notice actually that in this distribution, there is a gap corresponding to a certain value of ionization parameters, which is telling something about the existence of thermal instabilities that probably deplete the distribution of these components of outflow components at these specific ionization parameters. I will come back to this gap later in the talk. And we also have a general understanding that highly ionized outflows, they correspond to higher column density and are most likely launched very close to the accreting black hole. So very close means at the radius from the black hole event horizon of the order of a few tens of gravitational radii. Now, for historical reason, why we call the more moderate, less speedy outflows warm absorber, the more subrelativistic, faster outflows have been historically called ultrafast outflows. A typical example of how a good marketing, a good name, is actually helping also to make you famous in science. So why are ultrafast outflows particularly interesting in the context of AGN feedback? Well, remember, kinetic energy outflows goes as velocity to the third power. So, you may already guess what I'm alluding to. Now, before I answer this question, let me stress that this kind of very subrelativistic outflows has been so far primarily detected with CCD resolution observations, because it's very high column density gas, and it's gas which is primarily being seen in absorption lines corresponding to either hydrogen and helium light transition of iron. There have been attempts and actually a few results of finding this kind of counterpart of outflows in high resolution spectroscopy observation of RGS. And I think there are only a few cases where we find consistent detection of these subrelativistic outflows in CCD resolution spectra with EPIC-TN and in high resolution spectra with RGS. PDS 456, the brightest quasar in the local universe, being the most notable example. So this is, in this moment, has been also primarily a CCD resolution dominated science, and this will dramatically change with the advent of microcalorimeter instruments like CRISM and New Athena. But why are we particularly interested in this phase of AGN outflows? Because, we can detect outflows that are probably due to the AGN, so are powered by the AGN at all wavelengths. Not only in X-rays, we find outflows if we look at spectra in the optical. We find molecular outflows if we look at the spectra of molecular lines. And actually, if we look at the mass outflow rate of these outflows, the outflows that we detect in X-rays have actually very tiny contribution with respect, in terms of mass outflow rate, with respect to other kind of outflows. But if we look at the kinetic energy outflow rate of these outflows, actually, thanks to the third power dependence on the velocity, these outflows, the subrelativistic outflows, the red points in this plot, they have the largest kinetic energy outflow rate. And there is a sort of magic parameter space in this plot where theoreticians are telling us if your outflows is in this triangle, it's likely to have sufficient kinetic energy to be able to produce AGN outflow. Now, happens only if these outflows are able to couple efficiently this energy with the interstellar medium. And that's by far something which is not trivial, because these are outflows that I produce, as I told you, very close to the black hole. But if you want to have an efficient feedback effect on the host galaxy, you have to transfer this energy of scales of the order of kiloparsecs or tens of kiloparsecs. So can we efficiently transfer this energy from the scale surrounding the black hole to the host galaxy? And actually, can we prove that actually this transfer of energy occurs? Now, this happens if these outflows are energy conserving. So these outflows, at some point, they will hit the interstellar medium and create shocks. And in these shocks, if they lose a lot of energy, if they are efficient cooling in these shocks, they lose all your energies, and they then are unable to propagate this energy efficiently to affect the star formation in host galaxy. But if they can conserve their energy, they will potentially be able to do that. And just a simple calculation on momentum and energy conservation suggests that in an energy conserving outflow, the outflow of the momentum at larger scale shall exceed the outflow of the momentum of smaller scale by a factor of the order of 10 to 20. So the trick is very simple. We take a galaxy with a subrelativistic outflow in X-rays. We see if there is a potential counterpart of this outflow in the optical or in the submillimeter, and then we compare the momentum outflow rate of the two phases. And actually, if the momentum outflow phase of this phase on the larger scale is much larger, this is an outflow that has a potential of being responsible for feedback. And this is actually what this plot is doing. And now if I connect with ideal lines, the phases corresponding to the same sources, there are cases where actually we do see the expected dependence, the expected evolution of a momentum outflow rate for energy conserving outflows, and others where we don't see this evolution. And my posit is that the reason why there is this confusion is not only due to the fact that nature is varied as different, but also due to the fact that the measurement in X-rays are not accurate and precise enough. And therefore, this is another key field where we expect the future instruments, future microcalorimeter observation, to give a fundamental contribution to resolve this question. Now, there is a long way between still the outflow generated very close to the black hole and the scale where star formation happens in a galaxy. So can we fill this gap with other observations? And fortunately, we can do in principle by looking at spectra of AGN that are not dominated by absorption lines, but they are dominated by emission lines. In order for you to get a spectra, RGS, a spectra of an AGN of this quality, you need essentially to kill completely the direct emission of the AGN. As Andy Fabian reminded us earlier today, there is an easy way to do it, which is simply obscuring completely your source, your primary emission of X-rays coming from the AGN with an absorbing column density of the order of 10 to the 20 something. Now, this is said, to my biased judgment, the best signal-to-noise spectrum of an emission line-dominated AGN ever taken. This is already 20 years ago, is NGC 1068 taken with the RGS. And these lines are the clear signature for several reasons that I'm not going to enter into detail now, of photoionized plasma by the AGN radiation field. And this happens not only in this specific object, but in the overwhelming majority of obscured AGN, you have RGS spectra in the archive of. And just by passing a spectra like this are also a benchmark for atomic physics, for photoionized plasma. And Natalie explained yesterday why it's so important to get this kind of benchmark to inform our need of new laboratory measurements. Now, these emission line-dominated spectra are coming from extended regions on this order of 1 kiloparsec. They are also seen in optical through narrow line region and ionization cones. And in fact, the morphology of the X-ray emission and of the optical emission is spatially coincident. And that's kind of something a bit mysterious. You know, when we found these results with Stefano Bianchi 15 years ago, we were trying to understand how is it possible that you have so hot oxygen 7, oxygen 8 dominated gas, and actually gas also with higher transition that can be co-spatial with much cooler gas emitting primarily oxygen free. Now, this co-spatiality has been trying to, you know, there have been several attempts to try and explain it. And I think very recently, thanks to the work primarily done by a group in Israel, by Stern, Edu Bear, and others, I think we have found a solution how it is possible to have this co-spatiality of transitions corresponding to such different ionization state, which is radiation pressure compression. Let's imagine that you have a gas cloud where radiation is the strongest force applied, and at the external surface of the cloud, the radiation pressure is much stronger than the gas pressure. At the ionization front, there will be a sort of pressure gradient which will compensate the thrust coming from the radiation pressure. And in this region, the condition of the gas can cover actually a wide range in ionization parameter, temperature, and column density. And that's the region where we suspect the co-spatial emission of oxygen-free and oxygen-7, so optical emission line and X-ray emission line happens. Now, this is a very nice model because if it is true, the differential emission measurement, so the amount, the column density of each of the ionized component is determined only or primarily by the hydrostatic equilibrium of the clouds. So this is a parameter-free, parameters-free model. Either it works or it doesn't work. You cannot fit it. Does it work? Of course it does, otherwise I would not present it here. So we have applied this model to the 16 sources where these spectra are of sufficient quality for this measurement to be possible. And the result is in all cases, the emission, the differential emission measurements is consistent with RPC predictions. And there are a couple of indirect evidence that confirm that we expect that this emission to come from a region which is very compact surrounding the black hole, not from the whole extended narrow line region, but from a region of the order of 1 kiloparsec. X-ray lines correlates more strongly with AGN luminosity rather than with the luminosity of the optical lines. And also there are theoretical models that suggest this from happening. And there is a gentleman on the back who told me yesterday that his spatially resolved line profiles obtained with the Chandra high energy transmission gratings, they also essentially tell the same story. Now, all this is what we have been obtained so far, but of course, we are all looking forward to the future, and we are all working, if you have my age, you are probably working almost all of your time on the future. So let's see what CRISM and Athena in the future will bring. So first of all, a short reminder, why do we want to build instruments, build missions that contain microcalorimeter instruments? Because this allows us a leap, a giant leap in spectroscopic capability. These are spectra of figure of merit related to the weak line detection, measurement of strong line velocity and strong line broadening. And you will see the green curve is resolved. The orange curves are various instantiation of New Athena. And the other curves that are, of course, invisible by purpose are the XMM RGS and the XMM EPIC PN. So, of course, that's what we mean when we say this mission will represent an order of magnitude leap in our spectroscopic capabilities. So what can we do with them? First of all, we can highlight something that has remained a mystery, which is the outflow launching mechanism. We don't know actually how these outflows are launched, but we will be able to do it if we will be able to perform accurate measurements of the absorption line profile, because each of the possible mechanisms, thermal winds, winds driven by radiation pressure, winds driven by magnetic centrifugal acceleration, they'll give a different imprint on the shape of the line profile. which will be very easy to measure with Athena. For CRISM, probably we will be able to do it with X-ray binaries, much more difficult to do in AGN. But the AGN are also very variable sources, and there is possibility that these outflows, well, in fact, we know, we have measured, some of these outflows, they respond to the condition of the underlying continuum. And, you know, this is not very important if you look at very bright quasars with very high luminosity that are probably not very variable on the typical duration of an observation, but this will be key if you look at lower luminosity AGN, where you expect the variability to be on shorter time scales. And only with Athena, we will be able to probe this outflow on the dynamical time scale where you expect this absorber to vary. Of course, if you have a spectrometer associated with a good spectral resolution, you will be able to perform tomography, so spatially resolved measurements of a line profile, which are telling you not only the spatially resolved physical condition of the gas, but also study their dynamics. And last but not least, we will be able to perform, to have constraints on the geometry of the absorbing and reflecting matter by using the Compton shoulder, which is essentially the effect of single electroscattering that distort the shape of an emission line on scales lower than a few hundred electron volts, and that is strongly dependent on the column density and the orientation of the reflecting matter. And these measurements have been attempted with Chandra HETG observations. As far as I know, there is only one measurement, one positive measurement of a Compton shoulder in an AGN spectrum with the HETG, and will be routine measurements with an instrument like this. So, as a summary, I think I don't need to pledge to the audience that high-resolution spectroscopy has revolutionized our view of supermassive accreting black holes, enabled a deep understanding of the physics of AGN outflows, unveiled what I believe is a universally explanatory framework for hot photoionized gas in the nuclear environment, radiation pressure confinement, and probe the whole outflow chain leading eventually to AGN feedback. But still, with these extraordinary results, we still sorely need CRISM and New Athena to address a series of open questions that current data are unable to address. And with this, I thank you for your attention, and I'm glad to take any questions. Oh, sorry, this is just an aperitif, not only of lunch, but also of the first talk in the afternoon session from Missagh that will talk much more and in much more details about AGN outflows.
Thank you, Matteo. Question?
Thank you for fantastic talk. On the question of whether or not AGN outflows can do the feedback, you were talking about testing the energy conserving scenario by looking at X-ray outflow and then other color phases. What would you say about the time axis? Because I personally am not certain I would see the X-ray outflow at the same time as those color phases. So looking at one object is tricky. So what do you think about that?
Yeah, of course, you know, that's an indirect evidence, but it's the best we can do. Of course, once we will have a sample of some relativistic outflow with robust measurements, we can, for instance, also address the question of what is their duty cycle, you know, because, you know, these outflow, they seem not to be, except the PDS 456, they seem to be very transient. And this is a kind of weird thing. So I hope that this will be another important key for us to understand whether we are looking at the right smoke gun or not.
We have the first question live. So is the differential emission measure similar to that used for stellar coronae? Are these fully characterized by gravitational stratification? Is there a temperature dependence? Okay,
first question, I have no idea. Second question, yeah, I'm not sure that I fully understand the question, but probably the answer is no, because we are considering a very thin layer. So at that position, the gravitational potential of the black hole is essentially independent on the radial coordinates. And is there a temperature dependence? Yes, in a sense, the DEM is basically independent on the physical condition of the gas, in the sense that the dependence is smaller than the statistical uncertainties on our data. And in fact, the main element that affects the DEM is not the temperature, but is the whole spectral energy distribution of the AGN, which is responsible for the photoionization of the gas. In the paper by Stefano Bianchi in 2019, there are lots of simulations actually that show independent of the DEM under different conditions, SAD, metallicity, and so these questions are better addressed by looking at this paper.
Okay. In the context of the feedback, could you comment on the relative importance between the winds and the jets?
Oh, yes.
AGNs?
Well, the jets, of course, they are able to create very stronger but very localized impact. So on one side, the jets are very collimated. So we know from the images of galaxy cluster that they can create big disturbances on large scale, but they are very narrow collimated. So it's unlikely that they actually contribute significantly to the kind of feedback we are discussing here, which is the feedback on the overall star formation on the scale of the whole galaxy. In addition to that, of course, only 10% of AGN, they have relativistic jets. So the combination of these two things leads me to the conclusion that in this context of feedback, jets are not crucially important, so are less important than
jets and the winds. What kind of dependence on the AGN property? So you can predict, okay, here in this case, the winds will be more important than jets. Kind of,
yeah. Most of the objects I have discussed in this context, they are radio quiet, so they don't show relativistic jets. However, there is a paper from 10 years ago by Francesco Tombesi showing that there is a tentative evidence that radio galaxies could have a similar fraction of relativistic outflows as radio quiet AGN, but this is very tentative in this moment. Missagh, who is going to talk at the beginning of a session, he has a paper with Elisa Costantini a couple of years ago, where I think you studied the relationship between X-ray absorber and jets. So I think he's in much better condition of addressing this question. And maybe I leave up to you to comment during or at the end of your talk on what you found.
So there are two more questions from, okay, just one, but is there someone else want to ask a question which is not a usual suspect? Could be more inclusive? And Fabrizio.
Actually, mine is a comment, which I
so I relax.
I don't know. It's a question to myself and to everybody. I mean, if you take these velocities of these outflows seriously, and especially if you take the mass estimate seriously, the energy that you make in the life, I mean, in cosmological time, it's way like orders of magnitude larger than the galaxy binding energy. So we shouldn't have galaxies, essentially. Right. Or these phenomena have to be very, very short in time, which is possible. However, if that is the case, why do we see 50% of AGN with these things?
Sorry, 50% of AGN?
Of AGN with...
well, another thing you should take, I don't know if you factor this into account, but of course, AGN is also as a duty cycle. So we,
yeah, exactly. But then
so it's a duty, it's a phase in the life of a galaxy, and
exactly right.
And actually, only we believe that not the whole phase of a life of a galaxy outflows are important. Actually, only in the unobscured phase of the life of a AGN in a galaxy,
but also
outflow may be important.
What I wanted to add very, very quickly is that from the result I showed you before, it seems like all the baryons are actually within R200. A feedback of this kind would put, and in fact, this is what, when they put this feedback in simulations, they get metals out to 10 megaparsecs. And at least from this very preliminary result, it would seem like actually most of the baryons
Good
are
point.
within.
Yeah. But I think that, you know, the free parameter to play is possibly, you know, the AGN duty cycle and the duty cycle of this, of a relativistic outflow. That's why having a glimpse on the duty cycle of UFO is of course important.
Okay, thank you. Let's thank again Matteo.
And continue the session active galactic nuclei. I'm Maria Longinotti, and I was once a postdoc here in Lobes group with the HETG, so it's very nice to be back here. The first speaker is Missagh Mehdipour. He's going to tell us about probing multi-phase AGN outflows with high resolution X-ray spectroscopy, and this is an invited talk. So go ahead.
Thank you very much. Good afternoon. I hope you had a good lunch. So before lunch, Matteo gave a very nice overview of AGN in high resolution spectroscopy. So I'm going to continue that topic, but focusing more on AGN outflows. And the theme of this talk is on multi-wavelength view of AGN outflows, combining X-ray and UV information to learn more about the AGN outflows, and also making use of variability to study outflows, because that's a powerful tool to learn more about them. So, photoionization in AGN. So in AGN, we have a strong ionizing source that is illuminating nearby clouds. They get photoionized, and when we look through this gas, when our line of sight goes through this gas, we see the absorption features of this with our high resolution spectra. So to study them, we need to know the SED that is illuminating these outflows. We need to have good plasma models and atomic data to be able to model the processes that takes place in the gas. As we heard yesterday, these are important. And of course, we need to have observatories with high resolution capabilities to be able to resolve the features and study them. So I have a simple illustration of the regions that we are talking about today. So in AGN, we have the disk. In the broad line region, distances of light days from the black hole, we see disk winds. And further out, distances of parsec scales we have in the narrow line region, we see what sometimes referred to as warm absorber outflows or ionized outflows. I like to call them ionized because they're not that warm. So in the narrow line regions, the features that we see in the UV, often we see absorption from multiple velocity components. So this figure shows carbon-4. So all of these are carbon-4 absorption with different outflow velocities. And in the X-rays, we see a broader range of ionization. We see multiple components. So these are multi-component outflows. The lines appear narrow. Compared to what we look later on, these are less variable. Usually the variability that you see here is in response to what's happening with the ionizing SED. So this was the soft band. In the ion K band with Chandra, in some objects it's been possible to do high resolution spectroscopy and see highly ionized gas from ion 2526 that is possibly coming from a high ionization component of the outflows, but not always. Looking further down in the disk, what we start seeing in the UV is broad absorption. This is the case of Markarian 817, the STORM 2 campaign. So you see broad absorption, highly variable, and at the same time, you see a lot of X-ray obscuration. So I will talk about this more. So these are, here we are dealing with much more higher column densities and velocities than what we see in the ionized outflow. So velocities in the warm absorbers, we are talking about hundreds of kilometers per second. With the diskwins, we are in the regime of thousands of kilometers per second. And if we then go further to the to the UFOs, still diskwins probably much closer in. There are objects that have been reports of relativistic outflows, so the ultra-fast outflows, which in some of them, the UV counterpart has been detected. So these are, we see these different signatures of outflows at different regions. This is just this introduction of what we, of these different regions. The questions that we are interested is that how these outflows that we see in the broad line region are related to the narrow line region. Do they have a common driving mechanisms, or there are different mechanisms that produce these? So we want to map their ionization and velocity structures. We see a lot of variability in these. So we want to know what's producing the variability, what is varying, what parameter is varying, and then how these parameters of the outflows scale with the properties of the AGN, like the luminosity. And then what's the energy and momentum of these outflows? How does it propagate through the galaxy, and what's the impact on the host galaxy? So I mentioned variability is useful. So here I'm showing light curves from SWIFT, RKM 509, NGC 4593. So what's nice with SWIFT, you can observe it in X-ray, UV, and optical monitoring. And this monitoring is, especially when combined with spectroscopy, and definitely when combined with spectroscopy, is useful for studying the winds. But of course, also this timing studies is useful for disk and corona studies. So why variability is useful for wind studies? I think one good example is timing these outflows. So through time-dependent photoionization modeling, we can derive the parameters that are hardest to measure, like the density. So in this paper by Daniela, this figure shows some of these calculations comparing when we assume always 100% equilibrium versus non-equilibrium. So when the continuum goes up and down, what's the effect on the spectra that we see? So of course, now doing these times of spectroscopies with current instruments is challenging, and it can be done for few objects, but with future missions, it opens the door to do these studies. And of course, we want to measure the density and location of these outflows to measure their mass outflow rate and their kinematic luminosity. So I talked about variability. It's important to know what is varying when we talk about variability. So in that case, we need to look at the spectral energy distribution. So here I'm comparing 3 cases where we see different SED variability. So 3516, the whole continuum is going up and down. So all the components vary together. In the case of Mark 841, some of the components vary. So the hard X-rays remains constant, but the soft and the UV vary. So this actually has a different impact on photoionization modeling than the other one. Then you could have cases that there is obscuration very close to the ionizing source. So material that is located further out is not seeing the usual spectral energy distribution. It is seeing this SED, the obscured SED. And that has a very different impact on the parameters of the outflow. So especially when we are dealing with these obscurations, the study of the wind and the continuum emission is really interlinked. You can't study one without knowing the other. So it makes it more challenging and also interesting. So I mentioned 5548, that was the obscured AGN. Here, this figure shows the X-ray spectral hardness from Swift over a long time scale. So Swift has been observing this since 2005. It was launched in 2004. So this is not the flux, this is the hardness. So you see by eye that something has happened. At some point, there was a rise in the hardness ratio and a decline over the years. Of course, on short time scales, there is variability. So this is actually a change, a long-term change in obscuration because of of changes in the disk mean. So I'm going to show you. So if we look at spectra, high resolution spectra at different epochs, we can see how the wind has changed, which would give us useful information about the open questions that we are interested in. So in the next slide, I'm going to show you spectra from different epochs, when it was completely unobscured, when it was very obscured, and very little obscured. So let's start by these. So here are actually Swift spectra. I will show high resolution later. So as we expected from the light curve, in 2002 it was this normal unobscured state. 2013 very obscured, and when it's very obscured, you see the broad blue shifted UV absorption lines with HSD. They are outflowing with velocities of a few thousand kilometers per second. So this suggests the connection between obscuration and wind activity. And at the same time, so this is from the disk wind, because this material is shielding gas located further out, new lines appear. So the gas becomes less ionized. You see much more carbon-2, which is the low ionization species. And then when the obscuration gradually declines, the carbon-4 also becomes weaker, and then your carbon-2 disappears, starts to disappear. So what we learned from 5548, that there is a clear link between X-ray obscuration. So we are talking about transient X-ray obscuration in type 1 AGN and broadline region winds. What do we see in the high resolution spectra? Of course, when it's very obscure, the continuum is gone. So in the soft X-ray band with RGS, it's difficult to see absorption lines because the continuum has disappeared. So this is the spectrum with RGS taken in 2013. So what you see is the emission lines from the narrow line region, the X-ray narrow line region. But later on, as I mentioned, this obscuration has become weaker. You look at it with HETG, there is enough continuum. So you start seeing what lines are there, and you can study and model that. So in the case of spectra that are taken relatively recently, including last year, we actually do see absorption lines. So silicon 14, silicon 13, magnesium 12. And what we can learn from that is that this obscuration, while it is shielding gas that is located further out, lowering its ionization, which in some cases, people who explain line-driven winds require this kind of obscuration, not necessarily in Seyfert 5548, but in the quasars, where shielding is required to prevent over-ionization of the gas. When we look at 5548, it seems that there is actually a lot of ionized gas still in the warm absorber. So I will explain why, but this is likely a line due to the covering fraction and the line of sight. So whereas the UV warm absorber is in the narrow line region, perhaps the the gas that is in the Chandra, we see in the Chandra spectrum is located closer in. It's not covered by this wind. Here, I'm showing two independent measurements. So this is the equivalent of the carbon form from Hubble. This is the X-ray hardness ratio from Swift. Again, this shows a correlation between these two. And from modeling of this, we find a relation between the covering fraction of these outflows. So, so the x-axis is the UV covering fraction versus the UV versus the X-ray covering fraction. So again, in 2013, you see it was almost at some points fully covering the X-ray source, but it's gradually declined. Interestingly, at covering fraction of 0.6, there is almost little UV absorption because the UV continuum is a much more extended region than the X-ray source. So when you have an absorber that is covering 60% of the X-ray source, is hardly the covering fraction of the UV source is tiny. So this could explain in why in some of the objects you see the X-ray obscuration, but not necessarily the broad UV absorber. So putting this together, this is an illustration of what we think has happened in 5548. So archival studies, this is an archetypal Seyfert 1 galaxy, type 1, unobscured. It was like this. So we had the disk, we had the normal warm absorbers in the narrow line region. Something happened to it, and these outflows were ejected. They've remained in our line of sight, haven't gone away during all this 10 years. But gradually it has evolved. It's become more clumpy. It's worth noting that during this period that this was ejected, the SED, the ionizing SED, the luminosity is never changed. It's, nothing remarkable is going on there. It's so when we talk about this clumpiness gradually become clumpy, it's consistent with like some of these simulations that Daniel Proga and Tim Waters have been doing, that you start with some smooth outflow, and over time, because of thermal instabilities, the gas becomes more clumpy. So this is similar to what we see in 5548. Of course, it is still a puzzle as to what actually triggered this ejection. If you have something that, to the best of our knowledge and observations over decades, wasn't obscured and suddenly became obscured and remained obscured, what triggered it in the first place? So this obscuration has some important consequences. It leads to lowering of the ionization of the gas that is further out. The obscurer absorbs and re-emits. So in this paper by former students of Gary Phelan, they calculated what's the emission from the obscurer. Another important consequence of obscuration that is best seen in Marcan 817 in the Storm Tomb campaign is that they find the time lags of the UV emission lines has a dependency on the obscuration. So the perceived time lags is correlated to the obscuration, which is interesting. So when it's more obscured, it takes longer to respond. So as well as a line of sight obscuration that I talked about, there is a global obscuration. So of course, that absorption, I mean, our line of sight is not going through that, but is affecting the broad line region, the responsivity of the broad line region. So that's important actually, because the whole idea of reverberation mapping and the reconstruction of the broad line region and the measurement of the black hole mass is dependent on getting good reliable lags. So if these lags are kind of messed up by the obscuration, then we could get wrong results. So there could be objects that perhaps here we have something that is a campaign, we see what's going on, but you could imagine objects that are there is this global obscuration, but you don't necessarily look at, you don't necessarily see a line of sight obscuration. So this could in fact impact the GLAGs that you see. Again, in Markine 817 long campaign, you do see again a correlation between the obscuration, column density, and the equivalent of the carbon-4. So in this case, it's the column density changes that is driving the most of the X-ray and UV variability. So one interesting aspect of Markine 817 is that this is one of the first, or the first object when it's obscured, you do actually see in high resolution spectra absorption from this gas, from the obscurer itself, not gas that is further out. And in this upcoming paper by Fatima Zaidouni, she's going to talk about it more later. They find that the velocities minus 6,000 matches between what you see with RGS, different lines shown here, and with the UV carbon-4. Yes. So I mentioned Swift earlier. Swift has been useful to monitor more Seyfert 1 galaxies and look for these events. So it has been found in some of the other objects, through our monitorings. Roughly once a year, we find an event and we trigger. So I don't have time to talk about these, but I talk about 3783 because it's a GRISM target, PV target for GRISM. So what we saw with in 3783 when we triggered it is that the same thing as 5548, but also in the ion K band, we see new absorption that appears. Now, this is PN. Lines are blended with each other. This is this would be really useful to look with the GRISM. What I want to show in this slide is that, so I mentioned you see a high ionization component, you see a low ionization component. So what we see with these obscuring disk twins is that they are multi-phase, they are multi-component, similar to UFOs that are also found to be multi-phase. So this is a good example that Analia has published, Arias 17020. So in which a counterpart of it was also seen in the UV. So UFOs are also not just in the ion K band. They can have components in the soft X-ray and the UV, and like the obscurer. So the explanation that we think best work is that there is a primary UFO that is in training and shocking the ambient medium, and this results in the formation of other components that are weaker than that original UFO. So 3783, I mentioned 378 GRISM. So what we have here is features that we see with EPIC PN. We can't distinguish how these features are from each other. We see there is variability. So the continuum is varying and the obscuration is varying. The PN shows also there are features in the ion K band that vary. So we want to look at it with the GRISM. So here are some of the simulations using our best knowledge of this obscuration in this. So this is comparing unobscured versus obscured. So when it's unobscured in this scenario, you see the narrow lines. And when it's obscured, in this model, I've let the ionization to change of the narrow lines. So the narrow lines disappear, go into the soft band, and you end up seeing the broad absorption lines. But of course, we want the real data to know what's going on. At the end of the day, this is all still speculation. So, and this is a picture in the soft band. What's nice with GRISM is that it allows you to see the gas, the absorption in the soft band as well as the hard band. But with these observations, we still have proposed and got time with New Star to get the hard X-ray continuum. and Hubble to get the UV, because even though GRISM is going to help us a lot with the ion K band, it's not going to provide all the answers. You need those multi-wavelength spectral coverage. It doesn't have the like the hard X-ray continuum. You still need new stars. So there's a lot of supporting observations with this. I'm going to finish now with a few slides about the proposed ARCUS mission. So yes, in my talk you saw that I talked about UV X-rays. In the case of these obscuring winds, we need both, because when you have strong obscuration, then you see no lines in the X-rays. You don't have a good handle on the ionization parameter. So you can't constrain it, but from broadband modeling, you can constrain the column density. In the UV, you don't have a good handle on the column density, but you see some lines, you know what the ionization may be. So putting these together gives you a solution. So here are some simulations with ARCUS. Randall Smith is going to talk about ARCUS, I think, on tomorrow. So it allows us multi-wavelength high-resolution spectroscopy and monitoring within the timescales that we think 3783 is varying. And here I'm just the final slide. I'm comparing ARCUS with RGS and ARCUS in the UV with the HSD causing the oxygen 6 Lyman beta band. So with ARCUS, we can actually see both the narrow and the broad absorption lines, both in the UV and the X-rays, which is currently, if you want to do that with Hubble, first, you can't have simultaneous coverage with X-rays. You may get 1 or 2 observations. And also, so you can't track what's varying on the time scales of like 200 kiloseconds. Okay, so this is my, I'll leave you my summary because I'm out of time. Thank you.
Matteo.
Thank you, Missagh. Very nice talk. I have a question on the correlation between the covering factor in X-rays and UV. Isn't it actually, well, at least a possible explanation due to change or self-shielding of the gas, that when you have a lower covering fraction of the X-rays, you are essentially over-ionizing the UV absorber, and therefore you don't see it any longer. So it appears as a lower covering fraction, apparently.
Yes, so this is the question of how do we know, how do we know which component is varying? From spectral modeling in the X-rays, when we did these papers on 5548, I think the parameter, and Massimo Capi also published that we found that we think is most variable was the covering fraction. You can try to fit the spectral by changing the ionization parameter. So your question with the UV, I think from what we found in 5548, if it's a change in the ionization parameter, you would expect your line ratios to change, right? Whereas if it's a change in the covering fraction, you see, so it's been modeled. So when you model that, you see that it's a change in covering fraction. But I agree that it's very tough to know what is exactly varying, and because of this different component, really makes it challenging. And especially for the case of Markine 817, this is the toughest object to model, I think.
I have a question on no, I don't know if it was 5548. I think so. You showed the 2 carbon lines, carbon 2 lines.
5548, yes.
And then the carbon 4. And I was wondering, are the 2 components the same in velocity, carbon 4 and carbon 2?
No, so they are unrelated. So the carbon 4 is coming from this screen few thousand.
No, I know, but I mean, are there also 2 carbon 4 lines?
Oh no, well, this is the doublet.
That is the doublet, okay.
Yes.
And the velocity is different from the carbon 4.
Yes. Yeah, the velocity, yes, Definitely, yeah. So there would be a carbon 4, of course, from the warm absorber, which I'm not showing here. Yes, so this is a typical warm absorber velocities, a few hundred kilometers per second. Whereas this is, yeah, I don't have the velocity here, goes to minus 5,000.
Okay.
So different velocities, yes.
Other questions? Quick one.
Thanks for the talk. So I remember that this AGN, they show obscuration. The obscuration time period is like phases, like can be 1 day, half day, or 10 years, as in MGC 5548. Is there a correlation between this time of the obscuration with some AGN characteristic? I'm thinking about inclination, mass, or whatsoever.
Yeah, good question. So if you take 5548 and compare it, which is, as you said, 10 years, and compare it with 3783, they are essentially, they are similar objects in terms of inclination, in terms of the Eddington luminosity. So there is something that stands out that makes it an explanation. Yes, so I don't think there is this obscuration appearance of it is related to the luminosity of the AGN. Perhaps these are these MHD winds that suddenly appear. Maybe they are there, but not necessarily always in our line of sight, so they appear in our line of sight. Yeah, I don't think of course, the sample is also small, but as far as we know, we haven't found a correlation between some properties of the AGN. Yeah, that would be a good thing to investigate when we have more, yeah.
Thank you. Let's thank Missagh again. This here is Segura Montero, and this is a remote talk. He's going to tell us about detection of ultrafast outflow in a narrow line Seyfert 1 galaxy, Markarian 110. Omar, can you hear us? Are you ready?
Yes, I'm here. Can you hear me?
Yes, we can.
Okay.
I'll give you a warning, the 3 minutes warning. Okay, go ahead.
Yeah. Hi, everyone. Good afternoon. I want to thank you for the opportunity to talk about my work. I'm Omar Segura, a PhD student at the Institute of Astronomy at the Universidad Nacional Autónoma de México, UNAM. My advisors are Dr. Andrea Longinotti and Dr. Jair Herrera. And today, I want to talk about one of my works, which is the detection of ultrafast outflows in narrow line Seyfert 110. As the title of presentation say, I will talk about ultrafast outflows, but first, I would like to take 1 minute to talk about AGN feedback. So what is AGN feedback? AGN feedback refers to the mechanism through which a connection between the host galaxy and its supermassive black hole is established. This process involves the injection of mass and energy from the supermassive black hole into the galaxy interstellar medium. This possibility arises when an intense flow of gas produced by winds sweep the galactic bulk clean of interstellar gas and or hits it with enough energy to perturb the star formation. But what kind of winds can produce this perturbed star formation? Well, there are several types of winds, but I am going to focus on the ultrafast outflows winds. I want to clarify that from now on, I will call them UFO. These UFO have high ionization state values in logarithms of 3 to 5 Hz per centimeter per second, have a columnar density in logarithms of 22 to 23.5 per square centimeters, and have velocities of tens of thousands of kilometers per second, but that velocity can be higher. So thanks to the greatly improved X-ray observatories, the evidence of absorption lines spectra in the reference frames at energies greater than 7 keV in AGN spectra has increased. These features are commonly identified as hydrogen and helium-like absorption lines for highly ionized iron. Here, in the image on the right panel, I show the first detection of one UFO, Pons et al. For the AGN PG 1211 plus 143, identify one ultrafast wind with the detection of 3 absorption lines, namely sulfur 16, iron 24, and iron 25. And said wind has a value of 24,000 kilometers per second. Later, Tombesi et al. In 2010 and Gopher et al. In 2013 found in around 30 or 40% of nearby AGN's UFOs, and they suggest a probably origin from the accretion disk scale. So normally, if one UFO exists, this is what it looks like in a CCD resolution spectrum. But what happens if we move to the high resolution spectrum? Well, in the high resolution spectrum, what we will now see will be a greater number of absorption lines in the spectrum. Gradient spectrum offers more detailed diagnostic for absorption lines. And now we don't just depend for 1 or 2 or 3 lines in absorption. In the image on the right panel, we can see an example of what a high resolution spectrum with several absorption lines looks like. And now we can see that the things get complicated. So what now one should think about is how to facilitate the detection of these winds. Well, in our case, we use phase. Phase is one of the several code photoionization models that find the high ionization balance of one gas, creating absorption components that fit the Rayleigh spectrum, where each absorption component has its own set of parameters that describe the gas condition. The parameters that describe each component are: 1, the state of ionization, the state of high ionizations, which tell you how hot or cold the gas is. 2, the columnar density, which tell you how many particles per unit square centimeters you have. 3, the outflow velocity, which tell you how fast the wind is moving. And the last 4, the turbulence velocity, which tell you how broad or narrow the absorption lines will be. Here in the image on the right, I show how Longinotti and collaborators fits the spectrum as best as possible, except for the region from 18 to 23 Armstrong, where they choose to use phase. They found up to 5 different UFOS components in the narrowline Seyfert one. It has 17020 plus 4544 in 2015. And one of the important things is that each component has a different ionization state, columnar density, and velocity. Another but more recent example is that Kronglot et al. In 2021, where for the narrowline Seyfert 1 Markarian 1044, they were able to identify, with the help of phase, 4 different components of UFOs, where again, each component of the UFO had a different ionization state, different columnar density, and different velocity. We call the latter, that is having different values of parameters, a multi-phase ultrafast outflow. Here in Markarian 1044, the UFO1 had no energy to produce feedback. And I'm sorry, I forgot to say that here in Longinotti shows that the C component could also carry no energy to produce feedback. So Markarian 110 is a narrowline Seyfert 1 observed in the high resolution X-ray with the RGS instrument on the XM Newton satellite. This galaxy was observed 6 times, and we used the 4 observations of 2019 and the 1 observation of 2020. First, we add the 5 spectra to have a better signal to noise, and then we model the continuum, including the emission characteristics like oxygen A, Lyman alpha, and the oxygen 7 for our galaxy. Once we model the continuum, we noticed the presence of negative residual. So we did a blind search for individual lines in absorption. But why do we do a blind search for absorption lines? Well, although we can see some absorption lines by eye, that doesn't indicate that they are the only lines in the absorption. Moreover, when one takes out the significance, those dot lines may not be significant in the model for the data. So we do the search blindly and calculate its significance in the data of each line that appears. With this blind line search, we found 5 lines with a significance of 1.9 sigma or greater. These lines indicate the presence of absorbed gas in the data, so we decided to use phase photoionization code. Using phase, we found 3 components of UFO. These 3 components have different states of high ionization, color density, and velocity. In addition, the statistics indicate that each component is necessary in the data. So each of these components is marked with a different color in the absorption line that are identified with each UFO. Interesting thing to note for now is that the UFO A is identified as the UFO with the highest velocity, and the UFO C has the lowest value in the ionization state. Finally, we also took on the task for looking for UFOs in the low resolution data. In this case, with NuSTAR. In the NuSTAR spectrum, we found, okay, thanks. We found one wind with a velocity of around 68,000 kilometers per second to 84,000 kilometers per second. And this can be seen in the image on the lower right panel. The image on the upper left panel is a confidence contour for the absorption lines that we are identifying. And well, the conclusion are, for now, we found for now that in the XMM Newton and NuSTAR data, Markarian 110 showed a consistent ultrafast wind structure with at least 4 different absorption components, namely a multi-phase ultrafast outflow. Conclusive evidence of UFOs has been obtained through the simultaneous detection of a statistically significant narrow absorption line, and Markarian 110 is another new example of existing low ionization UFOs in narrow line Seyfert 1. Lastly, my work in progress is analyze the observation of PM from XMM Newton satellite, investigate if the detection of UFOs, of these UFOs, are capable of producing feedback, and analyze the other NuSTAR observations that are from 2019 and 2020. That's all. Thanks.
Thank you, Omar. Questions for Omar? Matteo?
Hi, thank you. It's Matteo Guainazzi here. Thank you for your presentation. The by eye strongest feature in the RGS spectrum are emission lines from oxygen 7 Lyman alpha and oxygen 8 Lyman alpha and oxygen 7. So 2 questions. Has this source during the observation been seen in a particularly low flux state? And the second question is, do you have any clues on what is the origin of this emission line? Are they possibly associated with any of the absorption component that you see in the spectrum?
I don't hear really well the question, but I think that I understand that. The first, well, the second, I don't any clue that that emission lines maybe came for the absorption UFOs that I found. And the first question, I don't remember really well what you...
The question is if any of these observations were taken in a low flux state. He's basically asking about the variability of your data, the variability.
Yes, if I don't remember wrong, the variability of this source with my 5 observation, that's not high. For that reason, that was one of the reasons that we had the 5 spectrum. there are no really high variability of the observation of the flux, observation of the five sources that I take, and that.
Yeah, if I can comment on that, it's like 20% of variations in the flux of the 3 observations that you've summed. So it's pretty safe to sum them. Other questions? No, we thank Omar again. Thank you, Omar.
Thank you.
So we move to the next talk. Next speaker is also a remote speaker, Yerong Xu. Are you listening to us, Yerong? He's going to tell us about ultra-fast outflow responses in highly accreting supermassive black holes. I'll give you a warning when you have 3 minutes left. We don't hear you. Can you hear us?
Yeah, can you hear me?
Yes, now yes.
Is
Whenever you're
my
ready.
slide?
Yes.
Okay.
You can go ahead, please.
Okay, thank you. Hello, everyone. I'm Yerong Xu, a PhD student from University of Palermo. Today, I will talk about ultra-fast outflow responses in highly accreting supermassive black holes. As previous speakers mentioned, we know that apart from accretion, AGN could also release its energy in the form of radiation, winds, jets, and here is a schematic plot including all kinds of AGN winds. In the X-ray band, we could observe warm absorbers and ultra-fast outflow we call the UFO. I'm also interested in UFO because, as its name says, it has the ultra-fast velocity and is usually highly ionized. So such kind of outflows could carry up a huge amount of kinetic energy, which might be sufficient to affect the evolution of the host galaxy, which means it could quench the star formation rate of the galaxy and affect the growth of the supermassive black hole. Due to the limitation of the current facilities, we cannot and may very challenging to directly observe the outflows in the extragalactic systems, but we could detect them in the spectrum. UFOs are usually detected with strongly blue-shifted absorption features. Here is a typical UFO detection in the X-ray spectrum of Quasar PDS 456, while the absorption feature comes from the absorbing gas outflowing on our left side. And the emission component results from the plasma misaligned with our line side. Although in the past 2 decades, people have detected UFO in many AGN, their launching mechanism is still not quite clear. One popular theory is the radiation-driven outflow, where the winds are accelerated by the strong radiation pressure. So it's naturally to expect UFO in highly accreting systems, like the upper right simulation shows. UFO could indeed exist in high attenuation and tend to be the equatorial direction. Another popular theory is the magnetically driven outflow, where the winds are accelerated along the magnetic field lines, like the bottom right simulation shows, tend to be the polar direction. Since today I will talk about UFOs in highly accreting systems, I will focus on the first scenario. There are 2 evidence for radiation-driven outflow. The first one was observed in a narrow-line 61 galaxy, R1324, where the equivalence width and the flux of the UFO absorption feature, in this case is iron 25 or 26, decreases with the X-ray flux. It was explained by the gradually ionized plasma in the strong radiation fields. And the other evidence was observed in both R1324 and PDS 456, where the blue shift of the UFO absorption feature increases with the X-ray flux, like the right plot shows. If we plot the UFO velocity versus the X-ray luminosity, we could observe the positive correlations between these 2 quantities. Since both these 2 cases are high accretion system, it suggests that UFO might be accelerated by the strong radiation field in high attenuation. However, this statement is drawn from only 2 cases. Then I will introduce a peculiar case of 1H0707 from my PhD first year's projects, which also motivate my foreign year's research interests. And by performing the flux resolved spectroscopy, we could obtain the UFO properties at different flux levels. The left plot shows the evolution of the UFO properties versus X-ray flux. We could find the current density and the ionization parameters are correlated, but the UFO velocity is anti-correlated with the X-ray flux. The last panel is interesting because it's opposite to the trend we observed in the previous two cases. We have explored several possibilities, but here I would just want to introduce our favorite explanation. 1H0707 was once estimated to have an extremely large adenine ratio, so it's a silver adenine source. The strong radiation field could puff up the inner part of the accretion disk, like the lower right schematic shows. When the source becomes brighter, the wind launching radius might be extended outwards, yielding a slower UFO velocity. And that mechanism could reproduce the anti-correlation we observed in 1H0707. So therefore, based on the results of this project and in previous two cases, two sources, we could say that UFOs in high accretion AGN are likely driven by the radiation fields, but it's more complex than we thought. Actually, we need a sample study to give a comprehensive answer and improve our understanding of the UFO launching mechanism. So before I introduce the results of my sample studies, I would like to mention several selection criteria. We have explored all the archival XM Newton data sets, especially on the RGS data, because we want to have the multiple absorption, UFO absorption features in the soft X-ray band instead to constrain the UFO properties instead of deriving the UFO properties from probably only one single absorption feature in the hard X-ray band by the APAC PN, with the lower spectral resolution. So the first, which also in the hard X-ray band, it might have some degeneracy with the relativistic reflection models. So the first requirement for our sample selection is that the target must be the type 1 agent without heavy obscuration, because if the obscuration will express the heavily express the soft X-ray band of the continuum, and it would be very challenging to detect UFO absorption features in the soft X-ray band if it's highly obscured. Then the second point is that we need enough statistics, which means enough counts to investigate the UFO evolutions at different flux levels. So it requires either we have the long exposure time on the source, or the agent is intrinsically bright enough. We set the criterion at 50,000 counts in the RGS spectrum. The last but the most important point is that we require they should have the UFO detection in their spectrum. So we manually set the 3 sigma criterion corresponding to the delta C stacks larger than 16 for our selection. So that based on this about 3 requirements, we could pick up 7 sources into our sample as well as the 3 sources I mentioned before. Then I will introduce a benchmark source in our sample, which is Maclaurin 1044. After modeling the broadband continuum, we performed the grid search of the photoionization model over the stacked time average spectrum of Magellan 1044. This method is performed to locate the global best fit UFO solution in the spectrum and could also help us to identify any potential multi-phase UFO solutions. And the scan methods has also been applied to each spectrum in our sample. Here on the left plot shows the scan results, and we could find the UFO is strongly detected in Magellan 1044. Then we perform the flux resolved spectroscopy. The middle plot is Gaussian line scan results over the flux resolved spectrum from the low to high flux levels. And we could observe that the blue shift of the UFO absorption feature becomes stronger when the source becomes brighter. If we plot the UFO velocity versus the X-ray flux, we could also find a positive correlation between these two quantities, suggesting that the UFO in Magellan 1044 is accelerated by the radiation pressure. Then we collect the results of the remaining targets in our sample. And here I just present the UFO velocity versus the X-ray luminosity. One discovery of our results is that we find previously unreported UFOs into AGN through our powerful grid search methods. They are IJ1034 and PG1244. Thanks to the large XM Newton campaign on these two sources, we can detect the UFO with a strong significance. If we look at the plot, we could find the slope between among these points shows non-negative values. So it means in our sample, UFOs are either accelerated by the radiation pressure or remain unchanged, probably due to the time delay of the momentum response to the source variation. Then if we fitted these points with a linear function in the logarithmic space and obtain the slope, and compare those slope evolution trend with intrinsic agent properties, we find an interesting behavior. We find that like the left plot shows, we find that in general, the slope of the velocity, which is kind of the acceleration, decreases with attendant ratio. How can we explain that behavior? In the standard accretion scenario, the UFO acceleration is expected to be stronger when the source becomes brighter. However, in the high attendant or super attendant regime, the situation becomes different. Well, we consider two possibilities. The first one is that probably the window long-term radius could be extended outwards, like I mentioned in the 1H0707 cases, and yielding the slower UFO velocities. And another possibility is that the UFO might be over-ionized in the strong radiation field and experiences the lower radiation pressure, which could also reduce the acceleration. We don't know which mechanism is the predominant one, but probably the reality is that the combination of these two mechanisms. And the last slide before the conclusion is that I want to emphasize the importance of the future missions such as Prism, Athena, and LEM or ARCOS for improving our understanding of UFOs. And the left plot, as Matteo shows previously, is that with unprecedented spectral resolution, we could directly distinguish the UFO-driven mechanisms through their line profiles, while the magnetic-driven outflow have an extended blue wing, and the radiative-driven outflow have an extended red wings. And the right simulation, the right plot is an animation of the LEM simulation for the UFO responses in the 1H1934 with at different flux levels with only 10 kilosecond exposure time. And it suggests that the large effective area of the future missions will allow us to perform the on-time spectral modeling of UFO without the need for the flux resolved spectroscopy, which could might smooth the wind features in the spectrum. So it will enable us to trace the UFO velocity properties both on time and on the different flux levels.
We are up to time.
Which could, thank you. And so the conclusion of my talk is that UFOs in high accretion agent are likely driven by the radiation pressure, but the acceleration may decrease with the increase in accretion rate. And that's all. Thank you for your attention.
Thank you. I'm afraid that we have to skip questions because we're out of time, so we can ask questions in the Slack channel. I have one actually. I will write it in the Slack. Thanks, Xu. Yerong. Next talks are, we have 3 flash talks. The first one is from Karthik Balasubramaniam about exploring Centaurus enigmatic giant radio lobes, preliminary findings from Chandra pointings. Are you ready, Karthik? Can you hear us?
Yes, ma'am.
Yes?
Yeah, I can hear you, but I'm not able to share the screen. Okay.
So you have 3 minutes.
Okay, can everybody see the screen?
Yes.
Okay, so good afternoon, everyone. Here I'm talking about giant radio lobes of Centaurus A started with Chandra. So Centaurus A is one of the closest radio galaxy, around 3.8 megaparsec. And you can see this is a mixture of various emissions. This is the galactic emission, intergalactic emission, and the its X-ray background. So you have different features. That is the filaments, voids, and substructures. And the northern and southern lobes are very giant enough. So you can see they're each corresponding to 480 kiloparsec and 300 kiloparsec passing line. And here on the bottom, you can see the Suzaku data with lobe 1 and lobe 2, which was corresponding in the Chandra patch here at S1 and S2. There you have a presence of non-thermal radiation, which is detected in Fermi-like. And the Suzaku pointings were detected with some point sources, and then they were removed them, and then the spectra was modeled with metal plus VAPS plus Pavlov, corresponding to local hot bubble, galactic halo, and cosmic X-ray background. There was presence of excess soft emission in both lobe 1 and lobe 2, around 0.8 keV with the StarWAS 2013. And they also say that because of the bad statistics and the poor PSF of Suzaku, it was not able to distinguish between the thermal and non-thermal radiation. So we have the Chandra data for this source. And here the 5 observations correspond to 97 kiloseconds. And the data was split into 3 bands, soft, medium, and hard, and then use wave detect algorithm to detect the point sources with the sigma threshold of 1.2 e power minus 8, that is a false of every 1 photon per 81 million pixels, and SRC plots with the assumed photon index and galactic volume density is used to extract the spectra and the light curve. And we also use the Beher package, that is for Bayesian estimation of hardness ratios for to calculate the hardness ratio and X-ray colors for 3 bands. And the detected point sources were cross-matched with Gaia, Allwise, and Tumas, and we can see there are around 140 around 214 sources with different sources detected with 3 bands, and there were no counterparts detecting galaxies. And in the combined hardness ratio plots, you can see that in the northern lobes, you have more of soft photon, and in the southern lobes, you have more of the hard photons. And with SRC flux, we can also see that there were few uh, uh, a few sources detected at which are cataloged before. And in summary, we would say that we have a consolidated pipeline to identify uncharacterized point sources for large scale studies of Chandra observations. And we find the giant radial lobe to be at a low X-ray countering region in the sparse northern lobes, and for soft X-rays, and southern lobes having hard X-rays. And this higher photon counts about 3 kV corresponds to either ionization or thermal processes, and then possible identification of previously undiscovered sources, and characterization is in progress. So, I'm also currently looking for positions. If there is anybody interested, please feel free to go into my archive ID or CV. Thank you.
Okay, thank you. We have seen it. So the talk is on X-ray spectral study of Macaria 421 using Astrosat observation.
Now, can you see my screen?
Yes, you have 3 minutes.
Yeah. Okay. Thank you.
So,
Yeah, thank you. So, hello everyone. I'm Jyotishree Hota, a PhD student from NIT Rourkela, India. So, today I'll be talking about X-ray spectral study of Mercury 421 using Astrosat observation. So, Mercury 421 is a high frequency peak type of laser. It is also a nearest and an extreme bright source which display strong variability across all the electromagnetic spectrum. And in this work, we use Mercurian data, which was observed from Astrosat during 2017 January 3 to 8 for a total observation time of 400 kiloseconds. In this work, we use time result spectral study, where we divide the total observation time into 10 kilosecond interval. The main motivation of this work was to obtain a more consistent physical scenario, which was responsible for the emission. So, if you see the synchrotron flux, we can observe by the observer was given by this equation, where F is the single particle emissivity and N of xi is the number density, which is solved numerically and is used as a local convolution model in XPEC. So, for a better understanding of the source Mercury 421, we developed two analytical model that is represented by N xi in this case. So first one is the energy dependent diffusion model, that is EDD. In this case, we consider our escape time scale to be energy dependent, and other one is the energy dependent acceleration model. In this case, we consider the escape time scale, so the acceleration time scale to be energy dependent. So the EDD model is given by this equation where psi, kappa, and normalization are the free parameter. And in case of EDA model, the free parameter are same as EDD, that is psi, kappa, and normalization. Further, to understand the dependency between the free parameter, we perform Spearman rank correlation study among all these quantity. For both the cases, the upper panel shows the scatter plot between the free parameter we are getting from EDD model, whereas the lower panel is shown the free parameter that we are getting from EDA model. So the upper panel left side figure is the scatter plot between psi and kappa, where we expect a anti-correlation between these two parameters. And as expected in observationally also, we are getting same type of result. In case in right hand side, we are that is the scatter plot between the normalization and kappa. Here also we expect a anti-correlation between these two parameters, and as expected, observationally we also getting same type of result. So further from this calculation, we calculate different physical quantity which was involved in the source. For example, for the scatter plot between psi and kappa, we can calculate the observed synchrotron photon energy. where we found the synchronous photon energy to be 5.75 keV, and also we found our other physical quantity, that is injection energy of the acceleration scale, to be 0.26 gamma. If we see the case of EDA model, here also we are getting same type of result that we are found in case of EDD. And in this case, if you see the physical quantity, then the observed photon energy we are find in this case to be 2.89 keV, and the injection energy of the acceleration region we are getting at 0.19 gamma. So in conclusion, we can say we have find the time result spectral analysis is a powerful tool to for the consistency of the model. Both the EDA and EDD model provide the insight into the underlying physical mechanism responsible for the X-ray emission in this case. So, and the correlation between the spectral parameters and the inferred estimation of the physical value can be used to constrain the model. So, thank you.
Thank you. So next speaker is Fatima Zaidouni. So tell us about AGN STORM for the emission and absorption features in the high resolution X-ray spectroscopy and 817.
Hi, everyone. So I work with Professor Erin Tara and postdoc Peter Kosets, and we are using high resolution X-ray spectroscopy to study the properties of the X-ray obscure in Markarian 817. So this small X-ray campaign is part of a much larger high cadence and multi-wavelength campaign called AGN STORM 2. It's a reverberation mapping campaign rooted around daily Hubble Space Telescope observations and other multi-wavelength observations. And it was designed to study and map the accretion disk of Markarian 817. So here you see the spectrum in gray of archival 2009 XMM spectra of this source outside of this campaign. And the source was unobscured then. But as of December 2020, in the beginning of this campaign, it was heavily obscured. And you see on top is the X-ray light curve from SWIFT, and the source underwent an X-ray flare, actually barely came back to the archival flux levels. And luckily, one of our observations overlapped with this period. In July and October 2021, the source here, you see the XMM and U-star spectra, came back to the more obscured state from December 2020. So most of the variability here is in the soft X-ray region, and that's likely due to changes in the obscuration itself. But there's also some variability in the hard X-ray region that is due to changes in the intrinsic continuum of the ionizing source. So can we study the kinematics and structure of this obscure? Yes, we can take a look at the RGS data, and you see here in blue, the April 2021 observation is a high flux observation, and you can see and distinguish the absorption lines of the obscure. While the other three observations, December, July, and October, were so highly obscured that the continuum was suppressed, and you can't see the absorption lines, but you can still see these narrow emission lines that are actually also present in the April observations, but are weaker because they don't scale with the change in flux. So the SED of the December 2020 observation here was modeled in the first paper of the collaboration, and zooming into the RGS data shows these narrow emission lines that are blue shifted by around 300 kilometers per second, so around warm absorber type velocities. And the SED of the April 2021 observation was modeled in this work, and the RGS data needed 3 photoionization models to account for all the absorption lines that we find. So we have a multi-phase outflow, and the blue shift was around 6,000 kilometers per second. So it's much closer to the black hole compared to the more distant emission line region that we saw the signatures of in the other observations more clearly. So without going into details, we also saw that the obscuration properties like ionization and velocity changes within the timescale of the observation. So very short timescales, which constrains the distance to about 1,000 gravitational radii. Not only that, but we also saw that the shape of the absorption lines changes between during this timescale, something that we could investigate better with CRISM and study the underlying model. This is a plot that Missagh showed you, where we see that the UV HST spectra and the X-ray RGS are consistent kinematically. He talked about how this connection extends overall in this period. And I will end there. And I encourage you to check out these papers and ask me any questions on Slack. Thank you.
Next speaker is a remote speaker with a contributed talk, Georgios Dimopoulos. Can you hear us?
Yes, I can hear you. I guess you can do it as well, right?
Yes. Okay, so I'll give you a warning when you have 3 minutes left, but please look at the video. And
Okay.
Okay. About exploring the nuclear environments of supermassive black holes using ray tracing simulations in the X-ray band.
Yeah, quite long the title. First of all, thank you very much, and hello from the Southern Hemisphere. I'm George, and I'm a PhD student at Diego Portales in Santiago, Chile. And when I sent this long title for the abstract for the meeting, actually, what I'm going to talk about is just talking about the new spectral models for AGN. And since I'm going to talk about models, allow me to do some introduction. So we'll know that there is a supermassive black hole in the center of AGN, and around it there is an accretion disk that produces radiation in optical and UV. Some photons of this optical and UV can be upscattered from the corona into X-rays. These X-rays can be directly observed or can be reflected in the circumnuclear material and can also be observed. This radiation can also heat up what we call the dusty torus and produce infrared radiation, and sometimes we have radio jet that produces radio emission. So if we move farther from the system, all these can be combined in one model, what we know the unification model, that more or less tells us that the different observing angle defines which type of AGN we observe. But if we move closer again, we can see that the material around the supermassive black hole can be distinguished into discrete groups with different properties. So we have the supermassive black hole in the center, and then around it it's the accretion disk. A bit farther, we can have the so-called broad line region that produces broad optical lines. A bit farther, it's the dusty torus, and we know that perpendicular to the plane of rotation of the supermassive black hole, we can have some polar material in forms of gas and dust, and a bit farther the narrow line region. So we know that the supermassive black holes are surrounded by material, so we need to study it, right? Some of the most common models that we use for spectral fitting are either slab models like PEXAF, Exmon, Silver, and Redhill. I'm pretty sure most of you are familiar with these. And there are also some toroidal models like Maltorus and Borus. And you can see at the bottom that there are plenty of different other models. But all of them have some kind of limitation, some advantages and disadvantages, either in terms of physics or in terms of geometry. So the slide that I had previously is a bit different from what we use as models right now in terms of mostly geometry. So this is our motivation, and we're using Reflex. Reflex is a ray tracing simulation code developed by Stefan Paltani and Claudio Ricci. And this has two very nice features. The first one is that it's fully modular, so you can have a pool of geometrical objects that you can place them wherever you want in the what's so-called the world of the simulation. And you can also define the physical properties of these objects, as well as the physical processes that can be in the simulation. So we use Reflex, and the first model that I want to introduce is based on the toroidal, the dusty torus that we have in AGN, along with the polar cone that we know, for example, that exists in the Seyfert galaxy based on infrared observations. And here is an image from the simulation of how it looks, the model. And we decided to call it Topo. Sorry for the Italians in the crowd. If I want to make a schematic of the Topo model, it's technically a corona that is above the accretion disk, above the supermassive black hole, which is the input source. And then after the sublimation zone, we have the torus that varies in terms of column density and scale. And perpendicular to it, we can have the hollow cone, which varies in terms of column density. So the three parameters of our model is the photon index of the source, the column density and the covering factor of the torus. The units are in logarithmic scale. The column density of the polar medium and the observing angle of the system. Now, when I introduced the material around the supermassive black hole, I talked also about the disk and the broadline region. So where are these in our model? So the next model that we are developing is called the AGN, and it's just an improvement, let's say, of the topo model. So we have the same three parameters as before, but now we have two more fixed objects. The first one is a slab annulus, which is the accretion disk. And in between the accretion disk and the dusty torus, we have implemented a broadline region configuration, which is like a flare disk. So it's a series of blocks with a logarithmic density profile to make it as realistic as possible. But these two objects have fixed properties. So here, just an example of the simulations that are being done so far. We can see that we can have different column densities and different covering factors, and all these can produce different shapes of spectra. But can we tell the difference between the different geometries? So here is another work that has been submitted actually 1 month ago, and today I got the reference report actually a few hours ago. So in this work, we simulated spectra for a Sirius galaxy based on Grism resolve. And Matteo before lunch mentioned that the Compton shoulder, which is this step-like feature a bit behind the K-alpha line, the iron K-alpha line, can be used as a probe to define the properties of the geometrical properties of the circunuclear material. So in this figure here, we used the full model of the Sirius galaxy, the AGN model, and then we decided to test some different models to see if they can reproduce the shape of the Compton shoulder. We can see, for example, that the spherical model cannot reproduce a toroidal geometry, but of course, we cannot tell for sure until we have real observations. So the RX spectral model family consists of the RX torus and RX torus D. The difference is that the RX torus D includes also dust in the torus, and it's ready to use. You can download it. And the RX topo and RX AGN are under construction. As you realize, it needs thousands of simulations to make the table models. So when the table models are done, we're planning to publish them and make them free, available for everybody, along with a paper that describes the whole process. And we have a huge pool of data that we want to use and apply these models on this X-ray data. So thank you for your attention. Don't forget that I'm talking about the circunuclear material. I'm trying to build realistic models. There are two of them that I'm building, the topo and RX-AG1. And of course, simulations are not real data. Thank you.
Thank you. We have time for questions. Any questions? So there's one from Javier Garcia in the chat. Can you expand in a bit on how the optimization is solved in this model? And also, do you include any line? There's a second from Javier Garcia. I'll read it now. Also, do you include any line broadening by the dynamics of the gas?
Okay.
Like in the accretion disk?
Okay. Because there is a panel. Okay, so the first question about the Comptonization. So the input source is implemented ad hoc. So we decide to include a power law with a cutoff, similar to the cutoff PL of XSpec. And this is the input X-ray spectrum. So we start from the X-rays directly. We don't have softer photons that they are being upscattered. So the model that I'm showing here, they're based on the public version of Reflex, which for now does not include any kind of velocity dispersion and kinematics and any kind of broadening, especially for the accretion disk. And so it's mostly focused on the obscured sources. But there is a version that we're building that will include these things, but it's not publicly available. And next models in the RX family will include any kind of kinematics. I don't know if that
Okay,
was...
thank you. I think we have to move on. I'm sorry.
No, it's fine.
Put your question in the
Feel free to ask me on chat.
Here, but in the Slack, you can put your questions. We thank the speaker again. Next speaker is also remote, is Alfredo Luminari. Alfredo, can you hear us?
Yeah, can you hear me?
Yes, he's going to tell us about the TEPID code, time evolving photoionization code, and perspective for future X-ray telescopes. I'll give you a warning in our video. Please look at it when you have 3 minutes left.
Okay, can you see the slides?
Yes.
Okay. So good afternoon, everybody, and sorry for this long list of remote presentation, but coming from Rome would have been quite long. So I will talk about time evolving photoionization with current and future X-ray telescopes, hopefully, using our newly built TEPID code. For this work, I want to thank many collaborators, in particular Fabrizio Nicastro and Yair Krongold. And I know Fabrizio is present there, so if you have, if you're happy about this model, you can ask a lot of questions. If you want to complain, instead you can go to Fabrizio during the coffee break. So I will thank Matteo Guainazzi and all the people that did the presentation before me, so I can go a bit short on this. This, by pure coincidence, is exactly the same figure he was showing. So, oops, okay. So sorry, I was struggling with Zoom. Okay, so just for pure coincidence, these are the same plots he showed. So here you can see basically that outflows are basically observed everywhere in AGNs, and they are suggested as the driver of the feedback from the AGN to the host galaxy. Here, the two examples. So on the bottom right, you can see the tight correlation between the mass of the central black hole and the stellar velocity dispersion and the mass of the bulge of the host galaxy. While on the bottom left, you can see how feedback from AGN is able to reduce star formation rate in high mass galaxy in agreement with observations. So again, just by pure chance, this is the same picture he took also for his talk, taken from a paper by 2019 by Smith. And as he was saying, what we want to do is to compare the energy of galactic scale outflows, which are those circled here, with the energy of nuclear scale outflows to ascertain the efficiency of the transfer from the energy from one scale to the other. So where is the problem here? Let us have a closer look to this picture. So in the case of galactic outflows, these are usually observed with ground-based advanced observatory like, I don't know, ALMA or optical observatories, which are able to spatially resolve the outflow and execute precise measurements. So you can see that here the errors are quite reduced. Instead, for nuclear outflows in the UV and the X-ray band, we have order of magnitude errors. This is because these sources are unresolved, and as Matteo said, these are also will be also unresolvable for a long time. And so most of the information has to come from integrated absorption spectrum across the whole source. We usually use the assumption of photoionization equilibrium, which, as Missagh was saying, basically encodes all the physics of the gas in only three main parameters, which are U, the ionization parameter, the outflow velocity, and the column density. So in this case, you assume basically the ionization source to be constant and the gas to be in equilibrium with the ionization source. In this case, everything is quite simple. So the most important parameter is the ratio between the rate of incident ionizing photons and the product between the density and the square of the distance between the gas and the illuminatic source. In this case here, the temperature is a function of U, ionic abundance also a function of U, and so basically you can build the spectra simply as a function of U. Then you have NH, which regulates the opacity, and the outflow velocity, which regulates the blue or redshift. So here are some examples. And you can see here that the phenomenology that you can have in your spectra is quite limited. So basically, what you can do when you measure observed spectra, basically you can extract these three information, U, NH, and V out. And this is, as you can imagine, it's a quite limited diagnostic. That's why it's almost impossible to constrain the gas density and radius separately from the observed spectra. And this leads to a number of key questions still open, and for the moment they cannot be solved. First one is, what is the exact location and the energetic of such outflows? And in the top right panel, you can see the lower and upper bounds for the energy outflow rate for a sample of UFOs, or disk wind, as you want to call them, observed in low-Earth Seyferts from a paper by Francesco Tondesi in 2012. And you can see the lower and upper bound have like 2 orders of magnitude. So it's impossible to meaningfully measure these outflows, and even more impossible to compare with galactic scale outflows. The other point is that we are not currently able to say if multiphase winds, which are ubiquitously observed, as also, for example, Missagh was saying before, are co-spatial, or for example, they are the segmentation of a unique continuous flow. Here I to put ideas or models have been put forward. First one is the one by Serafinelli, which has been discussed before, and the other is the very famous AGN unification scheme by Martinelli in 2000. So can we do better than time equilibrium photoionization? Of course, yes, because fortunately AGN are practically ubiquitously variable. Okay, so here in this example here, you can see the light curve of NGC 4051 from a paper of 2007, sorry. You can see that the count rate varies by a factor of 3 in the top panel. And in the bottom panel, you can see in red the gas ionization that you would expect if the gas were able to immediately adjust over the new flux level. Instead, in black, you can see what is the observed gas ionization. So here it is immediately apparent that the gas is not able to quickly readjust following luminosity variation. Indeed, as Fabrizio showed in 1999, it can be demonstrated that the equilibrium time scale is inversely proportional to the gas number density. So if you have a very low density gas, you have a very long equilibration time scale, as in the case we are seeing, and so you are outside the ionization equilibrium. Instead, if you have high density, then ionization equilibrium time scale is smaller, and you are closer to the commonly assumed photoionization equilibrium limit. So this dependency here is the key to directly probe the number density, and so to break the density distance degeneracy that we face when we use photoionization equilibrium codes. I don't want to go deep into all the equations. You can ask me after if you want. The only thing I want to highlight is here are the equations that drives the temporal evolution of our photoionized gas. And the terms highlighted in orange are the terms that linearly depend on your illuminating flux. Well, instead, the blue ones, those that linearly depend on your gas number density. So you can see here also that you are much sensitive to the gas number density, and this allows you to directly probe the gas density of the gas by looking at its temporal evolution. So with respect to before, when we were in the time equilibrium photoionization limit, here for time evolving photoionization, we have a much more difficult scenario. In particular, the temporal evolution of the gas ionization and temperature will show a strongly non-linear behavior, strongly dependent from initial conditions. You will have a response of the gas which is delayed with respect to the light curve. And also, under certain conditions, you also need to perform a separate time-evolving radiative transfer. There is no analytical solution known, and so that's why we built TEPID, which is our new code, which is able to compute the non-equilibrium gas ionization and time-resolved transmitted spectrum from the optical to X-ray. We submitted a paper in December, and we are confident that we are close to the acceptance phase. So we are going through the referee report. Here we just show an example of how TEPID works. In particular, here I simulate a very simple case in which you have a gas which is initially at equilibrium with a log U of 0.5. Then you have a very high flux period of around 10 kiloseconds, after which the luminosity is back to the initial value. So let's see what happens with the gas. Here I show the temperature. In particular, the solid darkest line is the evolution of the temperature for a gas of 10 to the 12 over cubic centimeters. In this case, the gas is so dense that practically is always in ionization equilibrium because its reaction time is practically instantaneous. So at the beginning and at the end, you have the temperature that you would expect in photoionization equilibrium with 0.5. And in the middle, where your luminosity is raised by a factor of 10, you indeed have the temperature you expect when you have log U of 1.5. If you decrease your number density, so for example 10 to the 8 or 10 to the 4, you observe two interesting features. First, the response of the gas is dampened, so the variation is much more limited, and also it's also delayed. Okay, so the peak of the temperature happens at later time with respect to the peak of the illuminating radiation. And these two very peculiar phenomenologies can be also observed in time-resolved spectra, as I will show you in a second. This is the same for ionic abundances of iron. Here I put 3. You can see that the densest gas here is the one that varies mostly. Instead, the tenuous one, 10 to the 4, practically is constant. So here I will also show, I don't have time to discuss on this, but what we include as radiative transfer is both the absorption of the incoming spectrum through both continuum and line absorption, and we also include the emission spectrum via radiative recombination continuum. What what I show is the hydrogen equivalent column density NH, up to which we obtain a very good agreement between tepid and the photoionization code cloudy when we run tepid at equilibrium. So you can see that as a function of log U, the limit log column density is quite high. So the code can be used practically for any NH which are typically observed in warm absorber and UFOs. Okay, so to finish, this is a brief demonstration of what we obtain after we run tepid and we compute time-resolved spectra. In particular, here, I start with a gas which is again in photoionization equilibrium at T equal to 0, but this time with a log U slightly higher of 1.5 because it's easier to appreciate, and the light curve is the same as before. So at the beginning, you have that the gas has the same absorption spectra regardless of the density, because by definition, we are in photoionization equilibrium. When you go to 2 and 8 kiloseconds, we are in the mid-time of the rise of the flux and in the decay. You can see that the 10 to the 10 gas, so orange lines, is in equilibrium photoionization. So the spectra are the same because the instantaneous flux in the two moments is the same. So basically you have the same opacity. So the spectra are the same, both in the soft and in the hard band. Instead, the 10 to the 6 gas is over-ionized. So at 8 kiloseconds, it has a lower opacity than it should have. Even after 6 kiloseconds, then the flux has returned to the nominal value. Still, the spectrum with 10 to the spectrum for 10 to the 6 is still over-ionized, and it will remain over-ionized until 300 kiloseconds. And now I cannot show here, but the 10 to the 6 gas will remain out of equilibrium for 300 kiloseconds. So this is easily detectable in any X-ray spectroscopic measurement with adequate resolution. Now we are also doing work in progress applying tepid to observation of GRB afterglows with XMM Newton. This is a work led by a postdoc at INAF, Ajvaraya Thakur. In particular, we are fitting some flux selected afterglows, and we are able to constrain the number density of the absorbing material and thus the distance from the GRB. And you can see that our values are clustered around the star-forming region-like overdensities, which have a density of 10 to the 3, 10 to the 4, and a maximum distance from the GRB, which is of the order of 10, 20 parsecs, which is exactly what you would expect, assuming that the long gamma ray bursts are generated by massive stars, such as O stars, which reside at the center of local star-forming region overdensities. So to conclude, equilibrium ionization, we always must remember that is a numerical approximation, and this approximation limits the constraining power of the observed spectra. Time-evolving ionization instead offers a unique channel to constrain the gas number density and radial location. TEPID is a novel model that can follow the temperature ionization of an out-of-equilibrium ionized gas and also produce time-resolved spectra, which can directly use it with Sherpa, Spec, XSpec, or whatever program you prefer to fit observed data. So these are the papers which are, the first one is already available on the archive, and the second one should be submitted within the summer. So our current steps are the analysis of archival data of XMM Newton. Yeah, okay, so I just leave the slide here. Thank you.
Okay, thanks. We have time for one quick question for Alfredo. Any question in the room or in the chat? Jelle?
Recently, Daniele Rogantini and Missagh Mehdipour have developed a similar model for specs, the TIFO model. Have you compared both codes to see how good or bad the agreement is?
Yeah, thank you for your question. Actually, we do compare the code. We reproduced the examples that are presented in Daniele's paper for an optically thin gas, and we reproduced the same metallicity, the same elemental abundances, and the same luminosity and light curve, and we do obtain perfect overlap. So we obtain the same temperature, the same cooling and heating, and also the same ionic abundance that were reported in the paper, which, if I'm not wrong, were oxygen and iron. So yes, we are perfectly in agreement.
Okay, thank you. Let's thank Alfredo again.
Thank you.
Next speaker is Daniel Wang. He's here. He's going to tell us about X-ray spectroscopic diagnostic of stellar and AGN feedback in the interstellar medium.
So I changed my title a little bit, so to make sure my talk is more focused. I promise you there's no cartoon, no formulae, real data. We're all looking for new generation of X-ray satellites, but we already can do a lot with existing data from XM and Newton RGS. As long as look at something bright nearby, then you can do kind of science, give you a glimpse of what we might be able to do with new generation of, say, instruments like calorimeter. Okay. So we're talking about the feedback. We heard a lot about this word, but mostly we're talking about how the feedback couples with ambient medium. So that's really the weakest link in our understanding of galaxy formation and evolution, really. So that's the astrophysics. And therefore, we just actually can give you some examples what can do with X-ray emission line spectroscopy. So I focus on emission lines, not absorption lines. Okay. Okay. So first example is the Dorado Nebula, which is the largest brightest H2 region in local group of galaxies. And it's well studied in all wavelength bands. Therefore, we know the stellar population, age, initial mass function, etc. So this is a nice laboratory. You can understand how the feedback works with ambient gas. We know the energy input, know how the feedback couples with the interstellar medium, producing X-ray emission, as you've seen, filling in all the cavities in this H2 region, so-called. So we already learned quite a bit by analyzing the CCD data from Chandra, from Suzaku. And so we know the gas is not isothermal against people's assumption, so like the single temperature. So, but also the log normal distribution seems to be a very nice categorization of the temperature distribution. So I encourage you to use the log normal, go beyond the single temperature model. And we can constrain on the mass loading based on the abundances of the hot gas, for example, and also the how much energy in thermal gas plus kinetic energy in the cooler gas, and compare with the energy input from stars. So this is all nice, all things be nice. But looking a little bit more carefully with RGS, this spectrum has been there a long time, nobody looked at it. Then you look at spectrum, very nice spectrum, look at it. Here you can see a kind of close up of the oxygen lines. This is a hydrogen-like one, and plus the helium-like triplet lines. What you find here is, for example, the forbidden line here, triplet of forbidden component is stronger than resonance component. So immediately tells you the kind of CRE assumption is not good. because for collisional excitation, you expect the resonance line to be stronger for the kind of temperature we are talking about. Okay, so immediately say, okay, so CRE assumption is not good. Okay, so say something else is going on, which you will not explain the forbidden line for the here. So a simple model here is combination of kind of temperature, kind of CRE plasma plus the charge exchange of the same plasma. So that's a very simple model. It gives a good fit. So you see the kind of combination of the two with the different lines gives nice fit of the spectrum. So this is kind of one story to tell. We're still working on the paper. This is the published work based on also RGS data on the active star forming region in the disk of the M51. This is called star forming active star forming galaxy. Again, you see the I focus on this helium-like oxygen triplet. Again, the forbidden line is stronger. It's universal. Every time you see a spectral RGS spectrum, any nearby galaxies, any star-forming regions, forbidden line is always stronger. Okay, this is universal. So I claim charge changes everywhere. Okay, so you have to be deal with. So we don't understand X-ray emission, diffuse X-ray emission well enough. So first task is to understand the nature of X-ray emission before you can infer any properties of the plasma. That's number one lesson. Yeah. So that is we can go on, look at the whole galaxy, famous galaxy like M82, and you can look at spectrum, very nice, beautiful spectrum. As you hardly probably get stars, you can such spectrums. And look at the oxygen helium triplet again. Forbidden line is clearly stronger. Okay, nobody cared about that. Then, so that cannot. This means you have just CRE kind of plasma. So you have to consider something else like charge exchange. So this is a simple model here, one by one. So this is a RGS spectrum. So first you have continuum, which you do the point-like sources, okay, which is continuum. So you cannot remove in the RGS spectrum. Here is contribution from the thermal plasma, single temperature, which is okay, works okay. But clearly you see the line here, like an oxygen triplet is will not work. Then you have to have another component. The charge exchange is a very simple process. The highly ionized species ions in hot plasma at interface with the core gas steal some electron from neutral atoms, and the electrons will be excited state. The cascading down will producing the X-ray emission you observe. So that's a process similar like a recombination line, because cascading will populate the forbidden lines. Okay, so that's the basic process. So anything which cascading will have the large forbidden to the resonance line ratio. So that's so that gives us information very useful. Not only explains why normally soft X-ray correlates with the cold gas. That has been mystery for a long time. People have all the theories, shocks, mixing, but here we have at least one mechanism which we're very clear is charge exchange, which occurs at the interface. Because charge exchange cross-section is like 10 orders of magnitude higher than the Thomson cross-section. It's a very easy to occur. Yeah. So it's a surface effect. Okay, it's a tiny regions that gives you a new physics insight about the interface. Normally you would not be able to study because you have turbulence, etc. So because charge exchange is proportional to the ion flux getting into the surface, okay, at the interface. So that gives a handle on this very extreme complex physics. That's you can learn about that. And now talk about how about the AGN feedback. Again, I'm not talking about AGN how the energy gets out from the AGN, but how the energy couples with the ambient gas. So this is probably one of the best example of analogous case like Hiroshima bubbles. You heard about Fermi bubbles in our galaxy. But there's a lot of confusions with disk materials in our galaxy because we are inside disk. So this is probably the best view of what might be happening, kind of Eurosita bubble like, but in external galaxy, you get like a bird's eye view of what's happening. So this is galaxy very similar to our own in terms of mass, in terms of overall star formation rate. And then you can see that here is a radio, is a low far depth, very nice bipolar structure, plus X-ray, you see the Chandra X-ray, similar configuration. Clearly, you have association or energy input from the AGN, which has jets, which is misaligned with the minor axis of galaxy. It's pointed right there. So, but jets could be precession, okay, process, producing this S-shaped enhancement seen in both radio and X-ray. So that's a real picture. Then look at the RGS data. Okay, so this is RGS spectrum. Okay, of course, RGS spectrum is dispersed spectrum. Is a convolution of spatial distribution of the emission with line response function of the instrument. So, but the spatial information is still there in the data. You can recover it, assuming the Doppler effect is not important. So actually, for isolated lines like oxygen 7, you can map out what is distribution spatial. Then you recover because you know how the line is dispersed. Okay, so that's actually the oxygen 8. Oxygen 8 distribution. Okay, around the so-called anomalous arm, which is due to the coupling of the heating of the jets or outflows from probably from the wings. And then you can do more. Actually, you can divide the regions into, say, for example, here, 8 regions, the assign spectrum to each of the region and combine the wavelengths, corrected one, dispersed one, combine into one together, then fit the spectrum. That's what we do. Okay, so it's kind of you need some coding to do it. That's still something we are working on that. Then, of course, it's not perfect. So you get a nice spectrum combined together, but you can still get residual for the forbidden line there. So this is purely just single temperature for each region. It's not sufficient. Then you can actually figure out ways to, okay, let the so-called G ratio to be free, then to fit the triplet and also the hydrogen-like oxygen lines. You can do that. So there's so a lot of information you can extract from the RGS data. So I just gave an example. This is the case. But how about even the M31? There's no star formation in the middle, no AGN right now. Then this is a Chandra spectrum, right? So a lot of point sources, that's we don't care. Remove them, and you see a diffuse emission, kind of bipolar outflows. But there's no AGN there right now. But there could be an AGN in the past. AGN comes and goes. So take RGS spectrum in the middle. Wow, beautiful spectrum, right? Then you actually turns out, I will not get into details, kind of run out of time. You find G ratio is high. It's not a CRE, okay? It turns out there's a lot of diagnostics can use include not only the oxygen triplet, but also different high-level transitions and the iron lines. So takeaway is the spectrum is best explained by past AGN, which was on for some time, reached ionization equilibrium, photoionization equilibrium in the plasma, and turned off. Then plasma still recombine, produce spectrum you observe. So the information is there. So you can fit just simple model on, off. Then you can figure out what was the luminosity of the AGN, how long ago it was shut off. That gives you here the luminosity. Here is about 500,000 age. So we predict basically there was the AGN there 500,000 ago. So the plasma is recombining over the time. So this is kind of running simple using a plasma with the way observed in diffuse gas. And it takes time. Okay, so the bottom line is recombination continuum, which will be observable with a future telescope, very easy to observe. And the second, the time scale for recombination time scale is very, very long, depending on density. Density, of course, decreases with radius. So it's takes the hundreds of million years in the outer regions of CGM. So if the AGNs like that, on and off, the plasma, you will never get into equilibrium. Okay, so that's, but that can be this history there. You can explore then to see how the AGNs, how frequent the AGNs on and off, in principle by studying the CGM spectrum. And so that's basically the future. It's complicated, but there's a lot of things you can dig out from data, existing data, and of course with future powerful instruments. So here are some takeaway messages. And so feedback is important. It's a coupling of feedback with ambient gas is a key in our understanding how galaxy formation is the evolution. And we can learn a lot about the feedback, the astrophysics, and the histories of the activities like AGNs, and the heating mechanism of gas. It's a huge amount of things we need to learn still. But here just gives you some ideas of what is coming. Okay, thank you.
We have time for a couple of questions.
Hey, interesting stuff. So you said it was on about 500,000 years ago. Since luminosity requires the volume, are you also able to estimate how long it was on?
No, because no. That's a little too much. Because as long as it's a simple model, it's a step function. Okay, so this now will not be as that simple. So this is very characteristic. Okay, how basically how bright it is. We need to assume kind of initial condition. Okay, it has to be reached kind of equilibrium. Basically, all the history be erased once you get the equilibrium in the photoionization, right? Then you get turned off. Of course, it could be gradual. Okay, so but characteristically, so just that's first step. Always, I think, tell my students, if you are the first, it's easy to do. Okay, whatever model you have, just as long as it makes a little bit sense.
So your decay is governed entirely by the spectrum itself.
Yeah. No.
But you do have luminosity scale. So
yeah, total luminosity at the beginning, which sets the initial condition of ionization. No. So plasma, there's no dynamics here. Okay, so plasma is according to what observed. So this is assuming the photoionization has no effect on dynamics. So the halo or the bulge, the hot gas distribution is still there, remains same. So we know we're using that distribution to calculate the ionization states at different different location. Yeah.
Two questions actually. Nice talk. The first one is the triplet. The forbidden line is always much bigger, but especially in one of your figure, I couldn't see at all the resonance. So my question is, could be also suppression of the resonance rather than enhancement of the forbidden.
In principle, resonance scattering could.
Yes.
But in the spiral galaxies, it's not normally it's not an issue. It's an elliptic galaxy, massive elliptic galaxies. I think will be important. But here we're talking about very dynamic velocity spreading pretty large. I would not expect. Well, I have not done calculation realistically. But actually, we don't have much information about the velocity. It's very much depending on velocity field, and depending on the total amount of gas at same temperature, which in principle could, yes, you can suppress. Actually, one of my students calculated the resonance scattering. If everything is crescent, it'll be important. But for very dynamic star forming region, it will not be important.
Okay.
Yeah.
Oh, okay. I'm done.
Yeah.
So I guess we can continue the
Yep.
discussion in the coffee break or in the Slack. We thank all the speakers of the session. Yeah. So we meet at 4:30 in this room after the coffee break.